and happy Ergoversary. I'm here to talk about our recent paper on optimal proof-of-work light clients. This is a joint work together with Zeta Varicchiotti, Matteo Maffei, Giulia Scaffino, Dionysis Stindos, and also myself. And in this talk I want to outline the idea of this paper and also present some of the results. So since we're talking about light clients, let us quickly discuss what are light clients and why do we use them. And for this, let's assume we have a population of full nodes where these full nodes are maintaining a blockchain. Now, if I come in and I want to participate as a full node, I need to connect to this network and I need to download the full blockchain, which is, if we think of Bitcoin, let's say, on the order of 600 gigabytes currently. So this might be fine if I run a full node on my desktop computer, but if I'm on my phone, downloading and storing 600 gigabytes might not be feasible. Especially since I most likely only want to verify some transaction has happened, or I want to check maybe my balance in my wallet. And for this, ideally, I don't need to download the full chain, but it's enough to download some chunk or maybe some proof that verifies these things. Another use case might be that I perform a transaction and then on another chain in a smart contract, I want to verify that this transaction has happened. And because I want to avoid paying too many fees, it's also a good idea that this proof should be very lightweight. And then with this thing, we can actually build bridges. And a bridge is essentially connecting two blockchains without using a trusted third party, right? We want to build it in a trustless way and also without the honest majority committee, right? So, and what we want to achieve is essentially we want to synchronize two transactions. So for instance, if I publish a deposit transaction to a bridge address on the source chain, I want to be able to withdraw some money from the bridge contract on the destination chain. And for this, we can use such a light client to achieve this in a trustless way. So this is kind of why we would need to, why we would want to run a light client. So now how does such a protocol look like? So a light client protocol is an interactive prover verifier protocol where we have a verifier that is connecting to a bunch of full nodes. And we can see that at least one of these full nodes needs to be honest, because otherwise they can just send us whatever. But this is the same assumption as if we connected as a full node to the network. So we also need to find at least one honest prover that we connect to. So then we ask them, what is the current state of the ledger? And they reply with some message. And then we can, from these messages, we can extract what is the latest state of the ledger without needing to download the whole ledger or executing all of the transactions. So in order to see how we can build such a thing, let's quickly take a look at blockchains again. And from work such as the Bitcoin backbone protocol, we know that there is a stable part of blockchain and an unstable part. And the unstable part essentially means that there exists some diverging view on this last part of the blockchain between different nodes. And note that even honest nodes could have different blocks here in this unstable part, and also that this unstable part is actually constant, right? So in this drawing it's 4, right? In Bitcoin folklore, this is usually taken to be 6, right? So we wait 6 blocks in order to have something be confirmed, whereas the stable part grows linearly with the lifetime of the system. So now what we are interested in our light client that we're trying to build is we want to output a block that is part of this stable part of the blockchain, but it should also be fairly new, right? So we don't want to output some very old block of this stable part, but a new one. And we call this block an admissible block also in the paper. And what do we want to achieve in terms of efficiency? We say that we are optimal, right, in the title of the paper. And what we mean by this is that the communication complexity should be constant, or it should be dependent only on what we choose to be this K. Okay, so with these goals in mind, let's see at how light clients are built currently. So what kinds of constructions we have, and let's look again at the blockchain, right? So the majority of the storage overhead in storing the blockchain actually doesn't come from the block headers themselves, but from the transactions. And in the block header, we actually only store a commitment to all of the transactions. The transactions themselves are organized usually in a Merkle tree, and then we store the Merkle root in this block header. So, as I mentioned, this majority of this 600 gigabytes is actually these transactions. So, a very simple idea could be, okay, let's just get rid of the transactions and only store the block headers. And then if we want to verify that some transactions is part of the chain, we can ask a full node to give us a Merkle inclusion proof of some transaction in some block. And then we can verify this, and we are convinced that this is actually part of the chain. And this has actually been proposed as the simplified payment verification in the original Bitcoin white paper. And this has a linear communication complexity in the lifetime of the system. So in other words, we need to store something that is linear in the length of the chain. Another idea is called NIPPAO, or also non-interactive proof of work. And the idea behind this paper is essentially that proof of work blocks are considered to be valid if they fulfill this proof of work inequality. And we can visualize this as saying, okay, the hash of such a block needs to have a certain number of leading zeros. So then we can observe that out of all of these valid blocks, right, if we think of this hash as a binary string, then we can see that half of these blocks will have one additional leading zero on average. Then a fourth of these blocks will have two additional leading zeros, and an eighth of these blocks will have three additional leading zeros, right? These so-called super blocks, they appear randomly, but we can somehow predict how many of them will appear on average. And then instead of providing the whole block headers to the light client, we only need to provide these super blocks. And since these super blocks are so heavy, right, it's sufficient to provide the light client with the super blocks. The light client can verify them, and instead of sending a linear amount of data, it is enough to send a logarithmic number of these super blocks. So this is all good and well. However, it's not compatible with the current systems such as Bitcoin, because it requires interlinking between these super blocks. So essentially, blocks need to link back to this to the last super block that appeared. Yet another idea is we can make use of zero knowledge proofs. So essentially, we have the blockchain, and we can create a zero knowledge proof that we can send to the verifier. The verifier checks it and can be convinced of some statements on this blockchain, or for instance, what is the current state of it. And this actually works, and we can do it in a constant communication complexity. So these proofs would be of constant size. And indeed, also the verification can be fairly efficient. However, there is quite the big overhead for the provers, because creating these proofs is quite expensive. Okay, so with this kind of related work in mind, let us move on to our construction. And our construction, the idea is essentially, okay, we are only interested in this admissible block that I said. So it's a stable block that is fairly new. So essentially, we can see that we are actually only interested in the tip of the blockchain. So why not make a protocol where the verifier connects to the provers and then asks, what are the latest blocks that you have? So give me a chunk of k+1 blocks, and I wait for you to send them to me, and then I just take these blocks and I take the first block to be kind of my stable block. So this is a a nice idea. It's unfortunately has some issues, right? Because if we only construct it like this, then an attacker can essentially create this chunk of blocks in advance, or it could simply take an old chunk and it could send it to us, and we would be kind of convinced of a invalid state, or maybe an old state. So this is not what we want to do. So we can kind of see that the idea to fix this would be, let us somehow force that this chunk is freshly mined, and then if we force this to be freshly mined, then kind of the rationale why this would work is that now the honest majority of miners will find such a proof first. So let's look at it. So first of all, how can we force such a chunk to be freshly mined? We can do this by introducing some randomness. So the light client, the verifier, which we call here V, inject some randomness to the ledger. And what does this mean? So this can simply be, for instance, okay, verifier creates a transaction that spends 0 coins to a newly created address that is random. And then the verifier sends this to the full nodes and waits for a response where there are k+1 blocks, and the first block of this chunk contains this randomness. So indeed, this would prevent that someone starts mining such a chunk in advance, because now they cannot, because they don't know the randomness, and also they cannot take an old chunk anymore, because also the randomness won't be part of the previous blocks. And then we can also kind of convince ourselves that the honest majority will find these k+1 blocks first. And since we accept the first proof that we receive, we should be fine, right? But the question is, are we really fine? Is this secure? And for this, let's look at the following scenario. Let's assume I'm the verifier. I broadcast this randomness to the full nodes, right? Some miner includes this transaction in a block, and the honest miners start building on top of this block. So now an adversary that, let's say, has a 49% mining power can create a fork in secret. So they mine secret privately on their own chain, where they try to fork out this randomness. And since this number of blocks is below k, right, they will be able to temporarily have a larger number of blocks with non-negligible probability. So with non-negligible probability, they can beat the honest miners, and they publish, so in this setting they found 3 blocks, let's say, they publish these 3 blocks to the honest miners, and the honest miners will switch to this chain. Simultaneously, however, the adversary will now switch to the abandoned chain that was previously mined on by the honest miners. And then they continue mining, right? So we can see that now the honest miners still need to mine k+1 blocks, because the randomness has not yet been included by the adversary. However, the adversary only needs to mine, in this case, 2 more blocks, because he's building on top of this chain that was already mined on by the honest users. So he needs to mine only these 2 blocks, where the honest users still need to mine these k+1 blocks. And we can see also in this example that in total the adversary needs to mine fewer blocks than the honest users in the same time. So indeed, a minority adversary can convince the light client of an invalid state of the blockchain. So indeed, this construction is not secure. And this is now where we come to our blink construction. It works very similarly, and it uses exactly this idea of broadcasting this random transaction to the network and then waiting for a proof. And the first proof we receive as a verifier, we accept it. But now the proof has to look like this. So instead of k+1 blocks, we now wait for 2k+1 blocks. However, the proof is k blocks, then a block containing the randomness, and then another k blocks. So now let's look at the rationale behind this. So again, this randomness is to prevent this pre-mining of a proof. The k subsequent block is in order to ensure that whoever mines this faster gets the valid proof. Together with the randomness, this necessitates some on-the-spot computational work, and a below 50% adversary will be too slow to find such a proof. Now, however, these k blocks before the the block containing the randomness are there to ensure that we go back and hit a stable block, right? So if you consider this attack from before, right, where we had the adversary mining on top of this abandoned chain of the honest users, we would be fine, right? Because the honest users, they had previously extended something that was part of the honest longest chain. And indeed, if we go back k blocks, we will be sure to hit a stable block, right? And so this attack is prevented. And actually in the paper we show that we formally prove that this construction is safe and we will hit the stable block with this proof. So yeah, this is the construction. We can take it one step further. We can, once we get such a proof and we accept it, we can kind of look at this first block as kind of a new genesis block. Because we know this is stable and it's fairly new, so we can start running an SPV on top of this block, and we start listening for blocks that build on top of this block, and then if we see that these blocks are part of the longest chain building on top of B, and they have k confirmation, we can also consider these blocks as stable. So this is kind of an extension on this Blink scheme. So now with this construction kind of explained, let's circle back to some applications. And here let's say that we are again connecting to these full nodes and we want to run a full node. So instead of downloading the whole 600 gigabytes, we could now download a 1.6 kilobyte proof, and we could catch up to the network. And then we could start mining from there or running an SPV from there, and we significantly save on the communication cost of this bootstrapping. Another thing we can do is we can verify historic transaction, right? We say we have this block that is safe, so it's stable and it's also fairly new, right? We know actually that all of the blocks before are also stable, right? So we can simply go back until we hit a block where we have a historic transaction that we want to verify, or we can also use some more efficient ancestry proofs and also use them to confirm historic transactions. Another thing we can do is we can use something like state commitments. And state commitments is essentially, if we think of a UTXO-based blockchain, right, the state is represented by the set of all UTXOs. So if every block now contains a commitment to this state, right, we could organize the UTXOs, let's say, in a Merkle tree and then store the Merkle root in these blocks, similar to how we store the Merkle roots of the transactions. Then getting a stable and new block would mean that we can actually confirm what is the current state of the blockchain. And this is something that is done in Ethereum proof of work, for instance. Although Ethereum proof of work is not a UTXO-based blockchain, but an account-based, but still they use a similar mechanism to commit to the state of the blockchain. And then if we have this in place, we can, on our phone, we can run this and we can verify payments, we can check the balance, and we can also verify any statement about the current state of the blockchain. So let's also talk about bridges again. How can we use this to build a bridge? We can build an optimistic bridge let's say Alice wants to deposit some money to the bridge address on Bitcoin and then withdraw some Ethereum from the bridge contract. What she can do is she can say to the smart contract, look, I've published a transaction on Bitcoin that is now stable in some block B. And then let's say there is a dispute period that starts. If no one disputes this statement, then Alice will simply be able to withdraw. But if there is a dispute, anyone can say, look, I don't believe you, prove it to me, here is some randomness, and then Alice needs to come up with a proof that consists of 2k plus 1 blocks and contains this randomness, and then if she's able to provide such a proof, then she can withdraw the money. And this is the rough idea. It can be made more efficient, by allowing other verifiers to challenge this, and then we combine somehow this randomness on chain, or we can also maybe use some on-chain randomness. But I think we can see how we can use this to build a bridge construction. So it can be quite a useful scheme for all of these applications. This anyway brings my talk to a close. I want to quickly draw back to attention the fact that we have a light client construction that requires only a linear overhead in terms of communication. In particular, we require a proof of length 2k plus 1. So for instance, if we assume k to be 6, we would require 13 block headers to send and verify, which is quite efficient. It comes, however, at the trade-off that we need to publish an on-chain transaction on the blockchain. So I encourage everyone to check out the paper. It should be quite accessible, and it contains all of the algorithms in case you want to implement it. Also, feel free to reach out to any of us or to check out the repository on GitHub, where we have a proof of concept implementation of this scheme. So with this, I want to thank you again for your interest in this paper, and have a nice day.